Well, I'm very happy to be at Strange Loop this year. Usually I'm on the other side of the screen. I would just like to give two thanks, because otherwise this talk would probably not have happened. So I woke up this morning unable to talk. With hindsight, going out yesterday in a very loud place where we were shouting at each other for hours was a very bad idea. So Jack brought me some lemon and honey, and I could speak this morning. And the other thing is my very old ThinkPad, which only had a VGA port. Turns out we have moved beyond. All right, who here yesterday was at the Concat language talk? Wow. Okay, cool. So it will be a similar topic today. I've heard of Strange Loop a few years ago, and the first talk that introduced me to the conference was Programming Should Eat Itself. And it was the first time that I saw a form of play with code that really resonated with me. And a few years later, I think it was, what's his name? Amar Shah, who gave a talk called Point Free or Die. And then at that point, I knew that I had found a place where I could exchange ideas on similar topic and find a safe place to talk these very esoteric, strange ideas. So I co-run a small design and research studio. We were planning on making video games, but we ended up with various circumstances to be exploring the failability of modern technologies. And we've been operating entirely from donated devices for 8 years. And it allowed us to explore how different devices fail and how we can repair them, these sort of topics. We're two, and my partner is not here today, but says hi. Some of these slides are Rekka's drawings. Together we make books and tools and games. We also sometimes document things that interest us with graphics, like trying to communicate things sometimes that is like a super dry topic with illustration, gives it more of a way for people to connect with this, and we've been doing that for a few years now. I am not an academic, and I don't think today I'll be presenting anything that's a groundbreaking technology, but I hope that you will enjoy nonetheless. So, I feel bad for doing another Alexander Saint-Exupéry reference at Strange Loop this year, because it seems that every talk that I go to has one. But in his book, Wind, Sand and Stars, Saint-Exupéry, who was flying, delivering mail, crashed in the desert, and he saw a fox who was eating one berry on each bush. And he was starved, and he didn't quite understand why the fox would only get one berry on each bush, even though the bush was full of berries. And I guess this talk is about that fox who just didn't eat every berry in one bush and then had the bush die. So the talk is it's not written there anymore, but so the talk I chose is awful. It's an approach to computing and sustainability inspired from permaculture. It honestly doesn't say much, but what I was going for initially, when you do like 20 iterations and everyone's like, yeah, this is good, and then you end up with something that, with hindsight, is just like, what the hell? Okay, so I'll break it down. An approach to computing, so I'll focus on computation, and sustainability is an awful, terrible word that doesn't really mean much, but what I mean by this is like sustaining a practice, like being able to do something for a sustained amount of time. And inspired by permaculture, which is also a pretty vague concept, but by this I just mean something that has a strengthening effect on the ecosystems. So my initial title was Computing Within Limits, but that's already taken by an amazing conference, and I felt bad using the namespace. So. Okay, so I'm interested in computers as a way to do more than consume, as a tool of creation, and for that reason I won't consider services or apps I think this talk is more about open specs, the knowledge to write your own software. I'm going to present technologies, but I won't give you their names because my interest is that you will consider writing your own implementation, develop your own systems. I'm not selling you on any one technology. I find solutions is a way of obfuscating knowledge. So like nowadays people shop for solutions and it creates a vacuum or like knowledge sort of disappear when you go from one solution to the next and have no understanding of the whole arc of the story. And you know, if you go on Stack Overflow, you're familiar with like, oh, just use library function X and you don't have to think about the problem. It's not portable. It doesn't equate knowledge. So this is not what I'm going to be talking about. I think there's this sort of like a myth that we're scaffolding on the shoulders of giant, but when you're all the way up there on the shoulders of a giant, it's really hard to steer it. Like, yeah. I think we should be careful on who makes these bicycles for the mind, sort of thing. So complexity, simplicity, sustainability, you go to all the talks here and it's always a recurring word and concept, and it's sort of like a very vague. Everyone has their different idea of what simplicity is. I'll use these ideas here, but I'll define it in a way that maybe makes sense. So let's say, unlike the vague goal of designing a sustainable product, I think like if you go in specifics where you're like, well, I'm going to design a product for disassembly. So that's a very specific goal. And so if I was to translate this to computing, I could say like software designed for disassembly has this inherent property that could be seen as sustainable. Do you know who that is? It's Kologmanarov, someone who was really into defining complexity and elegance. I think there's a few others like him that you might also be familiar with, but he inspired me a lot to look into defining what is a complex program, what is a complex system. I think his definition was that complexity in software is explained as the lowest number of instructions, rules, exceptions needed to achieve a given state. I mean, this is my interpretation of his work. Like he wrote a lot of stuff that came before software. I'm also interested in elegance. Elegance is another word for this index of complexity or simplicity. Elegance is sort of found in between, and it's defined in terms of limits. The best phrasing I've seen for elegance is articulating the value of absence. And that was a very vivid explanation of a word that's kind of like a hazy concept. So one last concept that I want to tie within all this before I move on is the idea of sabotage. Oh, hello? Okay. It's the idea of sabotage. So sabotage is defined as the withdrawal of efficiency. And you might be familiar with the concept, you know, from the Luddites and the people who were like clogging machines. And the Luddites wanted technology to be deployed in ways that made work more humane and gave workers more autonomy. I think if we can agree that technology is only worthwhile as long as it benefits society, well, to give people power over the technological system that rule their life and take them apart is extremely important if we want to have a system that goes beyond solutions and includes knowledge and the whole narrative that should encompass software, because software is not just an app that you download, but it's also like an understanding of solving a problem. So if we put these three concepts together, if we're hoping to do something for any sustained period of time, we'll want to match our computing system to meet the complexity required as closely as possible. It's a very obvious thing to say, but just watching, having conversation with people here who use massive tools to solve really simple problems, designed to. I spoke with someone earlier who like their personal website was using all this crazy tech stack that was designed to scale for like massive systems, but like I think like reducing to addressing the core problem that they were trying to solve is sort of like not really in trend or like out of fashion a little bit, and so we're moving away from elegance when we give into these things. When I made that slide, it looked good on my laptop, but now that I look at it from here, it's kind of a mess. So I'd like to acknowledge that everyone's situation is different. Obviously, my interest in software doesn't. I'm not saying that it should be like the silver bullet. It's addressing a specific scale of problems, and I think so. If let me see how I can phrase this. So let's say everyone has different limits, and what I would like to advocate for is that people find these limits and create solutions to address that directly. But we can sort of find limits that we all share with each other, and those are pretty simple things like the amount of water that you might need to survive, shelter, water, these sorts of things. As a metaphor, we can use like tap water. So, for example, if you have tap water, it has like unbound amount of water that can come out. If you have water tanks, then you can see how much is left. Knowing these limits allows us to plan. Companies now have made a whole business of hiding these limits, and it denies us the ability to plan properly. So, like as a made-up story, imagine that you live on a spaceship. The spaceship is 10 meters long, or 30 feet, sorry, and 80 gallons. The ship has 80 gallons of water. And the distance you can travel on your spaceship is dictated by the amount of water that you can carry between these destinations. Obviously, if you think that you'll run out of water because you know the amount that you consume and how much you can store, well, you'll plan accordingly. Not knowing this would be critical to the success or failure of your project of moving. So I would like to present to you my partner and I, we live on a boat, and that made-up scenario of a spaceship is actually our situation. It is 33 feet long. It's a very small vessel. We've been aboard for 9 years now, and it's sort of like a really interesting research lab that allows us to see our waste. There's no obfuscation of byproducts. We try to find cyclical circular systems. So to give you an idea, we have 4 6-volt batteries. We have about 200 watts of solar. Those are hard limits. And I mean, maybe your intuition would be that, well, just put more water, put more solar, and extend these limits. But those always comes at a cost. And on a sailboat, the cost is immediate. So adding more solar panels means you have more windage, more chance of getting knocked down. If you have more water tankage, you can move. It's slower to move. It's harder to get away from storms. So you make these trade-offs, and we found as like a balance in all this that leaves us with very little space for computation. Enough that. Sorry, I'm moving ahead too fast for this. So just before I move on to other things. So this mascot, I put it there just as a fun aside. So in Japan they have mascots for everything, and they have mascots even for preparedness. And this is the bonsai character, and it's the preparedness rhino. I think about bonsai all the time. In Japan, it's common to find a bag next to the door, and it contains a bottle of water, a toilet paper roll, a few medical supplies. The idea is that in Japan, you can get an earthquake at any moment, So people always have a ditch bag ready. And this is a sort of resilience that is really interesting. I thought I mentioned it. All right, so I'm not saying that everyone should go on the ocean, that our situation scales, or that everyone would be happy in these situations. But I don't think that what we learn is especially tailored to sailors. Like there's a lot of portable knowledge in what we do that I would love to see elsewhere. So yeah, just hopefully. If you're interested in going sailing, come and see me. But no, seriously, this is all things that I hopefully. You can adapt to your own limits of your own ecosystem. If you live off grid, you might, or in an RV, or if you're on mobile, or even if you have intermittent connectivity. There's a lot of people now who are expected to be 24/7 on the internet, but their internet's actually shit. We sailed around the Pacific, and it's crazy how people expect everyone to have internet all the time. And there's a massive amount of people who are left behind when we design systems that expect the fastest computer all the time. So personally, when we moved aboard, we tried to replicate the lifestyle we had on land. So we were doing iOS development and 3D games and all that sort of stuff, and it fell apart really fast because the systems that we used would just go through our batteries. And we could not sustain the practice of computation enough that we were like, maybe computers are entirely incompatible with being nomads. So we considered just doing something else. But it's really nice, this field of computation that we have, and it's really hard to let it go. So we tried to see if we can reconcile the two in some way. What we found, the microphone goes to sleep. What we found was that what worked before still exists, is still out there. Like we just changed the ecosystems that we were targeting, but we found that a lot of the software that people used before, we could emulate, we can encapsulate, we could still use, even though the modern world had moved on. Like obviously, using Slack on the boat is not. It's not going to work. But RSC is still working, but it was like this for everything. We started to look into these old systems. We went looking for systems that we could repurpose, for systems that had disappeared, and we sort of walked back the history of computation to find where we could land. One thing we noticed is that a lot of this history of computation was forgotten. I was speaking with someone earlier, and it was there's no computation history classes, and you can't expect people to always do the work of to dig the ancestral past of how we got here. But it creates these myths. A lot of people think that the ideas that died, they died because they were bad, but it's almost never the case. When you start looking into these systems, it's always a social dynamic, politics that made it so people forgot. So when you go through this process, you end up doing all sorts of different emulations of systems. I was super susceptible to seeing what I could run on the computer. I noticed that even though those are emulated systems, they ran faster and had better battery usage than modern software that were native. I could draw, I could draw in HyperCard for longer than I could draw in GIMP. So that sort of changed how I was looking at this, right? You can do so much less in HyperCard, but maybe I could adapt the work that I do to fit within the constraints of these systems that are more compatible with our life on the boat. If you go through this legwork, you might even find that you'll want to make yourself at home in these systems. When I discovered Think Pascal, I was blown away by how good it was. It's an idea that most people are forgotten, but it's incredible. It's rich. Okay, so who here use monofix, like a monospace font when they program? It's like almost everyone. But there was an era where people programmed with Acme and these systems, and proportional font was the norm. And I really raised, like, I was like, why is this, like, the trends, the things that come and go, it's not because they're better, it's usually because it's like a la mode. But now that I've been, I made these 3D engines and stuff in Think Pascal, like, looking back to my system that used monofix font, I was like, well, now I miss Think Pascal. So this is just some messing around that I did with these systems, and it completely changed the style of the work that we did. So it was not just a matter of, you can either scale up and like get more batteries, get more solar, faster computers, or you can scale down. Like I was super satisfied drawing in black and white. So let's say we start to consider preservation. I found that preserving my work that is living inside the system was even easier than the other things that I did. So like we had these massive, PSD files and Krita files, and I had a harder time making sure that I would be able to like open these image files over a long period of time than these systems that are like frozen in time. Like targeting the NES, like the NES is a frozen platform. It's not going to be patched. So you can be certain that and it runs on there's implementation of emulators for it everywhere. So you can be sure that if you make something that runs on it, it will run forever. Looking into these systems, I stumbled onto others who were also interested in these things, and usually it's people who come from a place where they live in the woods, they don't have reliable internet, and they also feel like they've been left out. There's communities of people who see this as a form of an aesthetic, like drawing clear bounds on like what you're allowed to use in your craft communicates a message, and also other people who were like, well, let's prepare for when the infrastructure that we use starts to crumble. Working within these emulator completely changed the way I looked about computers. Like working with images, there was a trend in computation for a while where you didn't edit text files. You had these these systems that were image based, so you could navigate through states of the emulator. So it would be like a complete image. When I say image, it's like a keyframe of state. It's the pixels on the screen, but it's also the whole runtime. If I give you this image and you open it, you'll have the whole system at that time. Being able to fork the states of how I was working, I thought it was really cool. For like a long time, people would tell me, "Oh, you should try Smalltalk, and you should look into these image," and I didn't really see the point. But now with this, it sort of forced my hand. Like this is the Smalltalk image for my computer, like 2 weeks ago, and you can still run these systems. They run amazingly well. They're really well documented. That's Smalltalk 80. It's about I think it's 12 kilobytes of code, and in the Blue Book they say it's one staff year of work to implement. So before I was talking about like scale, complexity, that sort of stuff. That's an index of scale that is super tangible. If it's a year worth of work to implement Smalltalk, then what is a 1 week computer or like a 1 month computer? I was curious to find like the balance, I guess, or elegance that would mean that the systems that I implement in my future self would be able to look back and implement it as well. Personally, I find that a 1 year computer is probably like, I'm gonna hate myself if I have to re-implement it another time. But I could scale it down, like using Smalltalk. You're like, well, maybe I don't need this. So you figure out what your real needs are, and you make a solution that fits your problem. So looking into these various emulators, I began thinking about software preservation, because obviously you end up with inside these forums where people are like really into making sure that things are going to be playable in the future, and that really resonated with me, because I spent years making iOS games that broke, like Unity games that I can't open anymore, and each time these ecosystems crumbled, it felt like a failure. Like I was targeting a system that was so complex that me myself as an individual, I wouldn't be able to replicate, and so it was not really mine. It was just sort of like I made a product for someone else, and software preservation became sort of like at the core of our practice. I found like a really disturbing statistics looking into like writing this slideshow. It was Video Game History Foundation says about 87% of all commercial games written prior to 2010 are now unavailable, and this is a failure of our field. Like so I'm not a super fan of explaining it that way, but a dark age is when you don't have any information, right? Like we're in a moment in time when people spend their adult life making one game, and 5 years later it's unplayable. The RMs, the complexity of the systems, it goes away, and I feel the preservation of these things will be able to advise people in the future of what our life was like, what our interests were. And I think, from my understanding, like people who are looking into preservation, like they don't seem to say that the market will want to solve this problem. So we can't rely on these ecosystems to do it for us. And as an aside, this little PNG that says "because obsolescence sounds a bit scary," I had this on my computer for a long time, and I knew I wanted to put it on. It's on my website. I wanted to put it in the slides, and I was like, oh, I'm gonna have to make this all like source of like all the image that I used from the slideshow. Where the hell did I pick this thing? But I found it. It's an illustration by Jenny Mitchum, who works at the Digital Preservation Coalition. This image was embedded in a tooth that no longer exists, and it was shared. So like I don't have a Twitter account. I have no way of even getting to that tooth, and finding it. I think it was like prior to the time. Apparently, Twitter started deleting content. So even the people who should know better are like using these platforms that bit rot faster than we can preserve them. So like so if there's a few people who spec'd out like strategies to work in like digital preservation, and they sort of like break it down usually in these 4 categories. It's like migration, you port the code; emulation, like hardware implementation of like NES emulator; encapsulation, where Docker, I guess; and UVM. UVM is sort of like you do it from the start. You target a target. You develop for a target that is designed to be easily implemented. It's a way of making a system that people could make new clients for, and this I liked, and I was told that this was the idea behind Java. I have never used Java, so I am not sure I understood the feud or the things that was going on between the different implementations, but I think it's a similar idea. Does anyone recognize this? Wow, cool. So this is Another World, and this game lives on because it was targeting a VM of 20 opcodes. I think, yeah. So this is the instruction set, and implementing this means that you have a client that runs Another World. It allowed the creator of Another World to make the game run on all sorts of systems, but also when he moved on to other things, people were like, the spec was available. People had reverse engineered it, and eventually just became common knowledge, and people could port it to Pico 8, and this is going to be hard to like this. It's going to take a while before this project disappears because people have vested interest in like writing little emulators because they're kind of easy to write. There's many other things like it. Like, so this is the instruction set for the Seafaring computer, which was co-written by Alan Kay. So Alan Kay was interested in these sorts of ideas too. They wrote this paper called the Cuneiform Tablets of Computation, and it was sort of like, oh, like we could make a super small VM to run Smalltalk 72.6, and they reduced it to these opcodes. I don't think it was ever implemented, but when I saw it, it was like, oh, it's like another world, but for Smalltalk. So this is what I wanted. I think I'm never gonna write another Unity game, and even beyond that, like I want a way to encapsulate all the logic of a project and find its fundamental operations. And so porting a project would mean just translating the thin layer of emulation onto other systems. And I'd like to show you like how we went about doing something like that. So, oh yeah, I have a disclaimer. So this is a feeble attempt at making a portability layer for our games, and I should have led with this, but I am a terrible programmer. I am more of a, I guess, illustrator and musician, and programming sort of like came really late to me, but obviously you're gonna roll your eyes when you see the implementation. I'm not gonna run you through the implementation, but don't see this as I'm not vouching for this design. It's as best as I could make it, but obviously what I'm trying to communicate is the idea behind it. So the way we scoped it, we had this one game that I wanted to port. It's called Okuni. This is not my laptop, so I cannot show you what it looks like, but if you imagine VR, Call of Duty 3D game, it's not that. It's very, very simple, sort of like head over heels, if you will. So that was like one cluster that we wanted to be able to host. I had this website, and I thought it was like, imagine if I hosted my website on this VM, which is a very different idea than hosting a game. It would stretch the spec to be more versatile. Another world had a VM that targeted specifically this one game. I wanted something that would allow me to use maybe one programming language to do multiple tasks. I do all sorts of different things, and one of those was like, I have a pretty intricate website, and I wanted to make sure that I could just port it to this VM. And the last thing that we chose, what was it? Oh yeah, okay, so we wanted not only the game and its documentation that would end up on the website to be hosted on this, we also wanted the whole tool chain to be hosted on this. So so what I mean by this is like, right from the start, the language was designed so it would be self-hosted. Like the assembler would be like running on this. The text editor that I would be using to write the codes would be hosted on this. There would be no moving in and out of different languages to be doing these projects. It would be all using the same virtual machine. So this intersection at the middle would be the VM. So finding opcodes or like an instruction set that would cover this was its core. And beyond this would be like things that applications don't share with each other would be, we'll call it the computer system around it. So the 6502 is like the chip that runs the Nintendo. Well, it doesn't do any I/O, like it doesn't draw. It doesn't have a processing unit for graphics. So this is part of the computing system around it. So this is sort of like the line, the delimitation of the system that we chose. I'm going to show you some assembly stuff. Don't avert your eyes. So obviously, I had written a bit of assembly. I understood the concept. Like when our life sort of fell apart and all the computers we had like didn't work on the boat anymore. we for a while we were like, oh, we're going to make NES games. That's going to be our thing. And it's a great target, but we want a bit more. Like there's no mouse. There's a few things that we wanted to expand from this. But that was my introduction to assembly. And one of the first thing I did was writing an assembler for 6502 in 6502. And then I was like, oh, this is cool. I can live in that space, which feels more like operating power tools than trying to tell the computers to figure out what you want. But like assembly had this sort of like vertical, like one instruction per line. I wanted to have something that was more like a fourth. So like it'd be like a more readable. I didn't want to be doing 6502 like 8 hours a day. That seemed crazy. So all right. So this is the instruction set that we ended up with, and it's nothing special, but. So we decided for 32 opcodes, it seemed like a nice little, nice balance, a good number. That means that in a byte you have, the 5 bits for operation and 3 bits for other things. We decided for stack machines because I think when we were in that period of designing the VM, I discovered the programming language Joy, and like I couldn't. Not like this is I resonated so strongly with this way of programming that I could just not do this, and I realized that there's like a ton of different schemes that you can use for doing this sort of system, but that was what seemed the most comfortable for us at the time, and we had written a little bit of Forth, and it seemed like reading about Chuck Moore and his philosophy of design that really resonated strongly with us. If I say Forth, is there people here who have no idea what I'm talking about? Forth, yeah? One? Yeah, you can come and see me after. So, if you're interested in that kind of stuff, like don't go straight for a stack machine. Obviously, just go check out what's out there. There's like tons of different designs. Like just recently, I learned about the Warren virtual machines, and I was like, oh shit! If I had known, like well, I guess like looking into this kind of thing, you like it starts to unravel really fast. List machines are sort of like a forgotten art, but there's like tag machines, interaction nets. There's all sorts of different architecture that are super fun to use. One thing we almost went for, which I don't regret, but yeah. So Joy is sort of like a spaghetti stack kind of, well, maybe not a spaghetti stack, but it's like a stack of const cells. So if you're gonna rotate items in a stack, everything is a const cell. So rotating like this many items, you just changed 3 addresses. It's a pretty fast operation. It's a pretty fast operation because it reduces the amount of data that needs to be changed. In a system like the one that we chose, rotating 100 items is insane because it doesn't have this flexibility of cons. So yeah, just maybe like if you're interested in that sort of stuff, just don't go directly for stack machine because I said so. So if we're going to program this thing, it has to have a language, and I didn't want to have a compiler. I designed the assembly so I would be comfortable at that level. I didn't want to instantly have to abstract it and have like, oh, I'm going to write in C, so no. I'm just going to make like a really comfy assembly language. So I went looking for the criteria for a good language, and I hated it. So the criteria for a good language that I found was these 4 things, and it said, obfuscate how things work. The language always knows best. Go for a la mode aesthetics. You want library, package manager, and that sort of stuff. So and I was like, no, I'm going to make a bad language. And so the language had to map 1-for-1 for assembly. So that already restricts what I can do. In this search, okay, so coming to Strange Loop, I was afraid that my understanding of computation would be, well, people would see that I don't really know what I'm talking about. Because I watched Strange Loop talks and people have studied and tried it, and I've been doing this for 2 years, and I'm not really sure I understand it fully. So, but one thing I noticed is that programming, like obsessing over programming language, is a distraction from computer science. Like, everyone is, there's this big war going on here, and people are trying to find the one thing that will work. Like, in permacomputing, it's not like any one solution that people are looking for. It's an interaction between many things, and the resilience of a garden or a farm. It's like it's the load bearing of like distributing the I don't know, like this plant will fend off insects that attacks this one, and so on. It's like this ecosystem of many solutions. Finding one solution I found was sort of like a distraction from all this discourse, and coming into it from the outside, not having the words to look what I was looking for. I felt I didn't have so much to go with. Anyway, so this is called tacit programming. Sometimes it's sort of like, I'll try to explain. So you don't have to, okay, so I'm not going to teach you how to program in this. I just want to kind of give you a taste of what it looks like when I'm programming. But okay, so this is a routine. So it's a label. In fourth, comments are used to define the state of the stack before and after a transformation. So basically, oh shit, there's a mistake on the slide. So num, the first one, should have a star because it's the rune. Well, it's the way I've decided to indicate that something is a short. So this virtual machine operates only on shorts and bytes, and this is not how you write the comment for this function. So this is just the fib function. So there's a bunch of opcodes, and there's labels that just, the little OK thing is a jump, and there's not much to it. The assembly of this function is the one there. So if you're familiar with 6502, it looks pretty much the same. So like on the left, it's 6502. So it has some like what am I doing here? So adding two numbers and incrementing the result and storing it somewhere. It's exactly the same amount of bytes in 6502 as it is in the system I made. It's not very expressive, but it's a change from 6502 where everything is register machine. So like in this like super vertical way, I could write like programs like this that looks a bit more like an actual programming language than an assembly system. So I think this bit of code is actually the assembler. So the assembler is written in itself, and this is the bits of the image of the ROM that I use to assemble the projects. Bootstrapping like this was kind of fun. It gives you an index of complexity of the system. I highly recommend trying to do something like this. In this language, one thing that's kind of fun is that raw hex is just valid tokens. This is a coin that outputs exactly this. It's very small, and so you don't have to try to read it. This is just a hello world, but those are labels. When I assemble, it creates a symbols file, so just the address of labels and a binary of the program. Being able to jump between these two things, I think people call it structural programming. So the indentation of this file doesn't exist. I don't like there's no. I'm not modifying a text file. I'm modifying this sort of like the structure of the assembly. Oh yeah, so I'm going to show you a few things that are fun to do with assembly that I couldn't. I had such a hard time finding fun things to do with assembly that I decided I would mention a few. So optimizing assembly means sometimes to just find two opcodes that can be reduced. So let's say you have like a swap pop. Swap pop, let's say you have two items on your stack, you would swap, and you would pop the first one. Like this is exactly what nip does. So like in a program that you're using swap pop, I have a linter, and the linter would not let me assemble programs that can be reduced to like simpler graphs. Like in this example, I jump to a label and then instantly return. These two opcodes can be, like my linter tells me, these two opcodes can be reduced to this one, and also like, I could probably just move the function next to the other and it would just fall through. So, okay, what else can I do? I can do arity checking. So arity checking is kind of interesting. If you're familiar with factor, it's like, well, I don't have types, but I can make sure by counting the changes in stack depth of the operators of a routine if it matches what I predict that it's going to be. So it's not a very strong type checker, but it's a good way to catch a bunch of errors. And it saves me a bunch of time. So yeah. What is that? Yeah, so like at the back I have like so this is all the modification in the stack depth of all the operators. So this is what I use to sort of like make sure that the program is in check with the predicted stack that I give it. This is, so yeah. So pure functions in Forth would be functions that don't have any side effect outside of its word definition, and catching those is really interesting. I made myself a really strong, well, a very aggressive type checker, like arity checker, that I can define functions that will never write outside of that, like that will never have side effects, and that allowed me to move all the I/O and all the things that could be unpredictable in smaller spaces. And writing a type checker for assembly, I had such a hard time finding other people doing this that I think people think that assembly is very well, not very expressive, at least not expressive enough that you can write safe-ish programs. I mean, there's no types in this, but there's a whole bunch of ways of catching unexpected behavior. I have this system where I can just say, like, at any point in my program, like, this is what I'm expecting the state of the stacks to be, and just being able to do this, like, really helps me with my programming work. There's a whole bunch of more things in validation that can be explored, but I'm not, like, I'm still learning about all this, I wouldn't be able to explain or present many of those things personally, but Factor, Kitten, Strongforth are excellent example of this sort of gymnastics. I highly recommend you have a look. Okay, so the system is self-modifying, and it's very self-modifying. So von Neumann machines are sort of like a discouraged thing, because now everyone moved to Harvard architecture, but even beyond that, I think everyone is like, state is really bad, we shouldn't be, having states, we want boundary checks everywhere. Well, so I'm not that good with like, I wouldn't be able to implement like a very good system that is safe, but instead what I decided to do is to lean into self-modification. And Forth has a disadvantage because I noticed that you quickly end up using like registers or variables to do complex stack operation, and that is a form of global variable. I noticed that Forth was super compatible with self-modification. So, for example, in this bit of code, I cache a value in a thread in itself. So it's not really a global, and I can make sure that, so the arity checker can make sure that this is not modified by anything outside of this function. And this safety has saved me a lot of time, and also it makes for faster program. Like, if you're gonna juggle the stack like crazy so you can get the 6th item here, like, you're probably doing something wrong. But if you're gonna use variables in Forth to do something, then like, you're creating global states, and like, tracking this is also equally super hard. So I rather rely on self-modification to do this kind of gymnastics. Like, let's say if you have like a nested loop, what I usually do, from the entrance of the function, I write in the future of the program the value that I'm going to be needing. And writing in the future of a program is kind of an interesting concept. It's like, when the program counter hits the color, it's going to read it as literal. Like the value is already in the program, and it was written from outside the nested loops. So I don't have 6 items to shuffle to get it to the value I need. And yeah, anyway, this is more of the same. And I made myself some checks so I could well, obviously there's some operations you want to be unsafe, and so I have these like extra cases where I can be like, well, this is gonna fail. In some way, possibly. Oh, I think this example is especially awful. It's so you could quote an upcode, increment it, and get the next upcode later and run it. Instead of, yeah, I know everyone's like, but yeah, like I don't do it. Anyway, I'm gonna stop here with the programming language stuff. So. Doing this, we were looking into other things that we could do that were fun. So like my partner and I were really into like conlangs, like creating stories where the characters speak language that have syntax and grammar, and the syntax is not just random words, it's actually like meaningful concepts that they're communicating. And I thought it'd be kind of fun if from first principle, the assembly language could be communicated with sign language. So we created a whole sign language to communicate the language. And then we were like, oh, it'd be kind of fun if it has its own writing alphabet. And so this is not our invention. This is by Bruce Allen Martin, and it's the hexadecimal glyphs. And we're like, well, we'll work on this and implement our own. So now all the opcodes have their own alphabet as well. So we can make editors of programs that have all this like gibberish language, and I'm not there yet where like I'm writing my programs, my made-up computer programs and my made-up computer alphabet, and but who knows? It looks nice, and one last thing in these sorts of I don't know, like communications of data. So this is a sprite. This is just, if you're familiar with the NES, it's sort of like, okay, so the before last line, 10, you can sort of see how every pixel is sort of like 1 bit in a byte. So if I was to, I don't know, move the pixel left, it would be 20. But if we grew, so you're gonna laugh, but so my partner and I were sitting maybe at arm's length away from each other. I broke the Raspberry Pi server that we were using for sharing files, and I never bothered to fix it. So what we do usually is we just we just speak the assets out loud to each other. So, you know, you can imagine communicating this is just very fast. There's this scientist, I guess, Daniel S. Wilkinson, who found a way to communicate binary data in like more practical ways. And the scheme was that, okay, so let's say you have a short, and these are all the bits in the short, and you have a sequence of consonant, vowel, consonant, vowel, consonant. Let's say if we were to take all these bytes on the right side of the image, encoding them with the numbers and the vowels. In that image, I'm just going to go back. Oh, I messed up the colors. So my slideshow program runs on the thing, if you were wondering. But yeah, so this sprite asset, it would be Badis, Zurov, Lubum, Dab Dab. So, but like the alphabet, we're not there yet. We're not communicating the assets in that made-up language. Anyway, that's it.